So here's a quick video on the 5.3 packet, the second half that you guys worked on in class, based on the people that did respond on the forum based on what they said they had questions on. So here's number 7. We're given important information here. 55% of high school students participate in school athletic at some level. 5% of those go on to play NCAA college team. So 5% of the 55% go on. What percent of high school students play a sport in high school and go on to play in the NCAA? Well, this is two separate outcomes, so let's represent it with a tree diagram. So randomly select a student is what we're doing first. There's a 0.55 chance that they're a high school athlete based on the 55%. Now we know the only other possibility is that they're not a high school athlete. So 1 minus 0.55 is 0.45, a 45% chance of not being one. So given that they're a high school athlete, so now these are conditional probabilities, right? The probability of being a college athlete given that you're high school is 0.05. So to find that means that 95% of those athletes don't play. Now down here, if you're not a high school athlete, we're not given this in the question, but I'm estimating the probability is 0 that you're going to go on to play in college if you didn't play in high school. And 100% of the time, those people that didn't play in high school won't play in college. So let's look at what you do to find the probability that you're played both in high school and then in college. So the probability of a yes and a yes is 0.55 times 0.05, 55% chance in being high school, 0.05% of being college of those 55. So 3% of students play in college NCAA sports. A couple important things to notice. If we want to find any series of outcomes, we follow the tree diagram and we multiply the numbers that come along on the way. Now notice the probability of being a college athlete is affected by whether you're a high school athlete. So that means these are not independent events. Being a high school athlete affects being a college athlete. Let's look at number 8. The diagram is up here at the top. We're going to kind of skip over that. Feel free to reference it, but we just went over a tree diagram. So we based all these on what we were provided in the question and the complement rule. Now, the probability of good grades, we just add up all these numbers. Good, good, and good, because those represent all good grades. So adding them up. About 66% of the students in the study describe their grades as good. But what I want to get to is down here. The conditional probability. What's the probability of B given A? So what percent of youth with good grades are heavy users of media? So given that they have good grades, event A has occurred, what percent are heavy users of media? We apply this formula that's given to you on your formula sheet. So this formula means that what's the probability of B given that A occurred? Well, that means both events have to occur. So we represent it with their intersection. That means A and B both occur. And we divide by the probability that A occurs because A has to occur first for B to occur. So we find their intersection, that's both event and divide it by the probability of A. So the probability of their intersection is 0.1092. Up here you can see that they're heavy users, good grades, that's that number, divided by the probability of A, meaning good grades. That's what we calculated up here, 0.6566. So the conditional probability is 16.6%. Remember, this formula is given to you on the formula sheet. You don't have to memorize it. Okay, here's number 11, first trimester screen. According to this study from the New England Journal of Medicine, 5% of normal pregnancies get a positive result. That's a positive result that there's some abnormality. So that could be troublesome, right? We'd clearly want to avoid that. Let's look at state, plan, do, conclude, which is what you have to do the 4-step process for these problems. So state, you're going to state the problem. If 100 women with normal pregnancies are tested with the first trimester screen, what's the probability that at least one woman receives a false positive? That means the test says she has an abnormality when she doesn't. Now, key thing here, you see at least. When you see at least in a problem like this, think about the complement rule. So my plan here, instead of calculating the probability of 1 false positive plus 2 plus 3 plus 4 all the way up through 100, that would take forever. I know that the probability of at least one positive is 1 minus the probability of no positive results, because the only result not included in at least one positive is no positive results. So I can find the probability of no positive results. Now, I'm not going to draw a tree diagram for 100 different branches. That would take forever. So I'm going to visualize my tree diagram here. So for women with normal pregnancies, I'm going to find the probability of no positive results. That's 0.95. Now, imagine the tree going 0.95, 0.95. So first woman's 0.95, then the second's 0.95, then the third. So what we get there is 0.95 to the 100th for them all not having a false positive, for them all getting a legit result, for them saying that they're negative to this abnormality. So that equals 0.0059. So the probability of at least one positive is the complement, meaning 1 minus that, representing all other possibilities, 99.41. So that means there's over a 99% probability that at least one of the women with normal pregnancies will receive a false positive. And that'd be alarming. You don't want that to happen. That's going to put stress on the mother. That can make things worse, maybe make the pregnancy tougher, if nothing else, emotional distress. So they'd like to avoid that and find better tests that don't give these false positives, whether it's for trimester screen or for drugs. Okay, take a look at number 15 now. So this one involves a drug test. So positive result indicates that they use illegal drugs. So there's some key things here with details. So it's saying 4% use drugs. The false positive rate is 5%. That means they get a positive, but they're negative. And the false negative rate, that means they're positive, but they get a negative, is 10%. So what percent of people actually use illegal drugs? 4 steps, state, plan, do, conclude. Let's check it out. State what percent of people who test positive actually use illegal drugs. Now, this is a perfect tree diagram. This helps really organize your thoughts and makes it much easier and quicker for me to solve as well. So persons tested, that's the event we start off with. The percent that actually took drugs, we're told, is 4%. The percent that didn't take drugs would then be 96%, because that's a complement. Remember, they add up to 1 or to 100%. Now, given that you took drugs, the probability of getting a positive result, meaning it's correct, is 90%. 90% of those people who took drugs will get a positive result. 10% will get a negative. That's a false negative, meaning they took drugs, but they got a negative test result. Now, of the people who didn't do drugs, 5% will get a positive result, meaning a false positive, meaning 5% will get a result saying that they took drugs when they didn't. Obviously, you wouldn't want that to happen. Somebody might not get hired or lose their job. Now, the probability that they don't take drugs and they test negative is 0.95% that they test negative given that they didn't take drugs. Now, to find the ultimate probability, follow any branch. So given that the person took drugs and tested negative, there'd be 0.004 or 0.4% of the people. Given that they didn't take drugs and they tested positive, 4.8% would be our answer. Now, we want to know the probability that they actually took drugs given that they had a positive test. So keep in mind that's a conditional probability. Again, this is reflected in, this is on the formula sheet, so you don't need to memorize this formula. You just need to know how to apply it. So we take their intersection that they both occur and divide it by the first outcome, a positive test. So when we apply this, and here's the formula down here, we get 0.036 for the intersection, and we divide it by 0.036 plus 0.048, the probability that somebody tested positive. There's 2 groups that tested positive. And when we add that up, we get 0.429. So the probability of taking drugs given a positive test is 42.9%. So that's not a high. Given a positive test, there's a good percent of those people that are actually negative. So that'd be alarming. Okay, go back over this video, go back over the summaries, look through the lesson and look over the examples, especially for examples of mutually exclusive, independence. This will be on your quiz. Most definitely a tree diagram will be on your quiz, and everything else from 5.3.